Okay, hi. So as we move into chapter 11, this is a bit of a big chapter. There's really two major topics to cover here. And I have them listed right here, both body sensations, the somatosensory side of things, touch and haptics, but also the control of the body. So really, I think the theme here from the textbook perspective is that we are covering the somatosensory nervous system. So if you recall from our basics, the peripheral nervous system is subdivided into the autonomic and the somatic nervous systems, and that the somatic nervous system is further subdivided into the sensory and motor components. Now, technically, that also includes all of the sensory nerves, including the cranial nerves from the ears, the auditory nerve, the optic nerve from the eye, and things like that. And we've covered that in previous chapters already. And we're going to continue talking about sensory issues now, of course, with somatosensory content here. I've labeled this mechanoreception because that's really the theme here. If we think about the topic of how we introduced the term transduction before, and how the eyes, the photoreceptors, transduce light energy into nerve energy, and how the hair cells in the ear transduce pressure waves in the air into nerve energy. And here we're talking about mechanical stimulation of receptors in the body. One thing I'm going to do a little different here, though, is I'm going to talk about the sensory side first before we start talking about the control of movement, since that seems to be more of a natural continuation from the previous chapters on vision and hearing, whereas in the book, they save that for the second half of the chapter, but I'm going to start with that here. I think that makes more sense to me anyway. As noted, we'll call this the mechanical senses if you want to. We can also call it haptics. And haptics, again, just generally refers to our perceptual awareness of our bodies, though it in particular also incorporates the fact that our perceptual awareness of our bodies is used to help perceive certain properties of objects in our environment. So, of course, it's useful to understand why we have a sense of touch and how that works with receptors in the skin that respond to pressure on the skin. But we also have to realize that the purpose of our sense of touch is to recognize the properties of objects. We spent some time, of course, talking about that in vision, right? It's one thing to talk about how the photoreceptors work and what the receptors in the visual cortex respond to, but ultimately the question is, how do we perceive and recognize objects? Likewise, for our sense of touch here, we can talk a lot about the mechanical receptors that we have and how the signals are processed back to the brain, but we also ultimately want to understand how by holding and manipulating objects with our hands, we are able to perceive properties, which we can do quite well. Any simple perceptual experiment could easily demonstrate that a person who is blindfolded, but holding an object in their hand, can easily report accurately various characteristics that it has: the shape, the size, obviously even just what it is in most cases, but even other things like what it might be made out of. So material composition, right? We can detect whether something is made of plastic or a brick or stone or wood or metal, usually just by feel alone. And that's an interesting perceptual challenge to understand the particular tactile patterns that specify these kinds of things. So, but as it is with many senses, we have a lot that we can say about the neuroscience side of things, but solving the larger perceptual question is a much more of a bigger, difficult challenge. And also potentially beyond the scope of this class, because of course there's separately the sensation and perception class that would be the real place to try to tackle those issues. So I have listed here everything that we would count under the mechanical senses. So in the previous chapter on hearing, we did have a brief introduction to the vestibular system because we could see the vestibular organs in our pictures of the inner ear. But we also have our what we'll call touch or tactile sensation in the skin. And pain is going to turn out to be a separate pathway here with separate nerve endings for that. And then we also should realize that we have these similar mechanical receptors that are in the skin are also found in the muscles, tendons, and joints, which provide information about our body's position, which is called proprioception, and also our body's movement, which is called kinesthesis. It may not really be that important to have two different words that describe the position of our bodies signaled by the same receptors, but nevertheless, we have two different words for that. Now, we call them mechanical receptors because what happens is that, thinking in terms of the contact on your skin, when you hold something, I'll just grab a pencil here real quick, right? So the idea is that poking the palm of my hand with this pencil, there is direct pressure on the skin. And of course, that direct pressure is going to stimulate receptors in the skin who respond to that direct pressure. Likewise, of course, when I make a fist and I'm bending my fingers, I'm pulling the skin here and on the back of my hand and the back of my fingers. And so there's a stretch of the skin and a bending, a deformation of the shapes of the receptors embedded within the skin as I do that. And of course, as I move my hand in this way, in addition to the skin stretch and bend, there are receptors in the tendons and muscles that control my hand. And of course, that's also true when I talk about whole arm movements as well. And we talk about how the muscles around the elbow, for example, the bicep and tricep regulate the elbow position, that those are also stretching as our body moves, right? And so there are various muscle groups around each joint that stretch in various ways that will provide information about the position of that joint. So we're going to start by talking about the vestibular system, since we just covered the inner ear in the previous chapter. So one thing that I think I might have said about that before, but if not, the best way to think about the vestibular system is to call it an accelerometer. We oftentimes think of it as the sense of balance, and certainly it does play a role in our balance, but it is most accurately considered an accelerometer. So what we're talking about here is that as our bodies move, they are, of course, accelerating. And so providing some information either about the current position or orientation of our heads and our bodies, because the organs are located in our heads, we might say it's more about head orientation. But certainly, of course, head orientation is related to body orientation because our heads are attached to the bodies, of course. So in a way, it provides that kind of whole body positional orientational information. So it does, of course, play a role in our standing and walking balance, of course, right? So if I am trying to stand upright and I lean one way or another, this system is important in helping me detect that lean and compensate and make sure I don't fall over. It's something that, of course, we learn to do when we are 12-month-old infants, just learning to stand and walk for the very first time. But there's a few other things that we might want to think about going on here. So I'm talking about compensatory eye movements here. So think about this for a second. This is something called the vestibulo-ocular reflex. And so there are very tight linkages between the vestibular input and the visual input. And this is important when it comes to thinking about the midbrain and the superior and inferior colliculus that receive input from both the eyes and the ears. Something that we can do very well is imagine, this doesn't quite work in an online lecture setting, but I'm going to give, you can try this yourself. Maybe give yourself a target to look at. Like I'm going to take my pencil back here and I'm going to sit this in front of my face. It's about a foot in front of my nose here. And I'm just going to fixate my eyes at the tip of the pencil. And I want to keep my eyes fixed on the tip of the pencil, but I'm going to turn my head left and right like this. And as I turn my head left and right, my eyes have very little difficulty remaining fixed on the tip of the pencil. So that means for every head turn that I'm making, my eyes have to counter rotate to stay fixed on that location. And this is called a compensatory eye movement, right? And we do this all the time because we can be walking and our head's turning one way or another. And I look at something far away and I can keep walking and I can keep my head turning and I can keep my eyes still fixed on that distant object. This is, of course, a natural thing we do all the time. But in order to maintain that gaze or that fixation on a distant object, we have to, our eye movements have to simultaneously compensate or counter rotate for every other little movement of our body. And the vestibular system plays a very important role in doing that. And so this tight linkage between the visual and the vestibular actually helps us maybe understand why certain things might occur, such as when you experience motion sickness, such as from riding in a car or being on a big boat on the ocean or being in an IMAX movie or a simulator, virtual reality. Any of these things might trigger a motion sickness. And that's because what's happening here is that because this system is always trying to compare and integrate input from the visual system and the vestibular system, in those situations, there is now a conflict because if let's say if you're in a simulator, like in an IMAX movie or a virtual reality device, the visual information is very much consistent with what would be occurring if you were moving. But meanwhile, the vestibular system is telling you that you are sitting in a chair and you're sitting perfectly still. And that conflict now leads to a conflicting signal in that VOR is what it's called, the VOR system, vestibular ocular reflex. Now, of course, when it occurs on a boat, it kind of is the other way around in a way, because you could be below deck in your cabin and your vestibular system is telling you, I'm going up and down because it's responding to the movement of the waves. But because you're kind of in this room and you in the room are moving up and down together, the visual information is basically saying, I'm sitting in a room and it's stable. And so in that case, again, there's conflict. Now, why it makes people nauseous is something we don't entirely understand, right? So we understand the mechanism of when these things are going to conflict with each other, but we don't necessarily know why these conflicts result in people vomiting, which frequently occurs, right? But how does it work? So I called it an accelerometer. So let's explain this a little bit. So as I'm noting here, orientation with respect to, that's what the WRT means, with respect to gravity, but let's explain this a little bit more. So we have two parts of the vestibular system. First is called the vestibular organ, and then there's the semicircular canals. And that's what I had noted in the previous chapter when we saw the pictures of the inner ear. The semicircular canals were very apparent there, but there's also something else, the vestibular organ, which actually is also subdivided into two small parts called the saccule and the utricle. And so the saccule and the utricle are essentially small sacs of fluid. All right, let's jump ahead to a picture. This is showing us here at the very, very bottom, one of the either the saccule or the utricle, right? And so what we're seeing here is it's a rounded, kind of a sac-like organ filled with fluid, and floating around inside are these small little bony parts, right? They're called otoliths, right? Which actually stands for something like ear stones or something like that. I think that's literally what it means, right? Oto means ear and lith is referring to stones. So, and lining the interior of this organ, we see little hair cells. And these, of course, hair cells that are very similar to the same hair cells in the cochlea used for hearing, except now they are not stimulated by sound waves that make it into the ear, but rather these otoliths, because they are heavy, will sink to the bottom of the utricle or the saccule down there at the very base of the semicircular canals, right? And of course, when they sink to the bottom, that's because of gravity, right? So if I'm standing perfectly upright, that means the otoliths will sink straight down to the very bottom of the saccule and utricle. And if I happen to be leaning to one side, lean to my right or left, for example, then what's happening is those otoliths will kind of swish over to one of the sides, or if I was hanging upside down, the otoliths would essentially sink to what is effectively the top of the saccule and utricle. And so this differential activation of these hair cells, because of where the otoliths happen to be moving, will provide us information with what we will call our linear acceleration. So gravity, of course, is a linear acceleration. It's working on our bodies in a straight line, right? Linear acceleration straight down. Likewise, of course, if I were to start walking forward, think of what happens when you're in a car, for example. When you're sitting in a car and you're stopped, and then somebody steps on the gas really hard, and the car accelerates forward, you kind of go flying back in your seat a little bit, right? And the exact same thing happens to the otoliths here, is that if I'm now just standing upright and I start walking forward very quickly, the otoliths are sort of like the passenger in a car. They're just going to go flying back to the backside of the utricle and the saccule here. And so again, we're going to have that experience of, oh, I feel my body is accelerating forward now. It's a straight line linear acceleration forward. But not all of the accelerations on our heads and bodies are always linear. We also have curvilinear, and that's where the semicircular canals come in. If you can sort of tell a little bit from this drawing, the three semicircular canals are oriented in three different planes, perpendicular to each other. So you have this plane here, which is the sagittal plane of the head, right? And then we have this plane here, which is the frontal plane. And then we have this plane here, which is the coronal plane, right? And so we have those three horizontal planes, and we can also think in terms of the XYZ. So this is like the X, and this is the Y, and this would be actually, this is the X, I think, and this is the Y, and this is the Z. I get them all mixed up. But we can also call it, you can use aviation terms if you want to, pitch, roll, and yaw. So the idea is that when I nod my head forward like this, I am actually operating this plane, right? I'm operating in this plane, and I'm nodding head, and this is called pitch, right? When I'm doing this, I'm shaking my head left and right. That's called yaw, and that would be orientations in the horizontal plane. And I can also kind of do this side-to-side rotation, and that is then the roll. And that's in this plane of rotation. And so what's happening in this particular case here is that there's fluid inside these canals, and it's sloshing around in there. And if we notice at the base of each one of these canals, we see three little tips like this. And you come back here. It says here that they're filled with this jelly-like substance. I feel like I'm missing a word there, sorry. And these hair cells. So let's come back here. At the very base of each of the semicircular canal, there's this little tip that comes up here into this little round base. This is called the ampulla. And when in some drawings, it kind of looks like a paintbrush that's sticking up there, right? And what happens is that as that fluid, this jelly-like fluid inside the canals is sloshing around, if I'm doing this kind of movement or this kind of movement, right? It sloshes around in there, and it causes that paintbrush to essentially wave back and forth as that liquid kind of moves around in there. And of course, just like other hair cells, once they get pushed and pulled in various directions, that's going to stimulate these action potentials. And so the upshot of all of this, just to come back to the previous slide here, is that the saccule and the utricle provide information about these linear accelerations on the head, while the semicircular canals provide information about these rotational accelerations around the head. And so together, all of the various possible directional movements of the head can be detected by these organs, right? And so I can combine all of that stuff because, of course, as I said, I might be walking forward in a straight line while also turning my head left and right. So there's a combination of both linear and rotational accelerations working on the vestibular organs. And then, of course, if I want to keep my eyes fixed on some distant object, as I might do sometimes, all of that information can be used to help my eyes compensate, right? So that's really the gist here of how it all works. Now, the rest of the mechanical senses here, we can talk more about the somatosensory nerves. And so this is the nerves coming from the body, the skin, the muscles, and everything. So we're going to get, we can call it discriminative touch. This is what I was talking about before when I said that we can pick up an object and recognize various properties. We can detect temperature, we can detect patterns like texture, like I can feel if an object is smooth or coarse to the touch. And that's what we mean by discrimination here, is I can discriminate different textures and different patterns with these receptors on the skin. There might be a difference between soft pressure and deep pressure. So for example, if I just do a light press with this pencil tip on my fingertip, now I can just detect the feel of that. But anything that's more of a deep pressure, I'm going to use the eraser on my arm here, right? You can kind of see in the little video window there that I'm putting some pretty deep presses here. And so in addition to pressing on my skin, this is also hitting other stuff under my skin, right? I'm hitting muscle, I'm hitting organs of blood vessels and stuff under here as well. And so all of the stretching of all of those things can be felt, right? There are, by the way, stretch receptors somewhat similar to the ones in the muscles in your arteries and veins. Why in the world do you have a stretch receptor in your arteries? Because of blood pressure, right? And our body is trying to regulate blood pressure, and it doesn't want to be too high or too low, obviously. And when our blood pressure gets low, what happens? We feel thirsty, right? But how does our body know when our blood pressure is low? Because the stretch receptors in the arteries detect this constriction of the blood vessels, right? So that can also be activated, though, by that deep pressure on the skin. As it turns out, pain and itch are a separate pathway. Of course, there's other natures of sensations, like what's the difference between something that itches versus tickling, for example. And as I mentioned already, we have the position and movement of our joints. So let's talk about the different kinds of touch receptors in the skin. We have a few different kinds, so we can subdivide them in various ways. One subdivision here is to talk about what we'll call simple nerve endings. These are sometimes called free nerve endings. So these are just considered to be sometimes a bare neuron. But what does that mean? I'll kind of explain it in a second here. And then we have others that are elaborated neurons. And so these are neurons that kind of have modifications to them so that they respond a little bit differently here. And then we sometimes have these free nerve endings that are also kind of surrounded by other cells that are not neurons, but they're wrapped around other cells that can have an effect on its function. But they all pretty much do the same thing, which is that they respond in some way to mechanical stimulation, which I have listed here, the different kinds of mechanical stimulation. And then every time that stimulation occurs, we get the same sort of thing that would happen if they have traditional dendrites that were just activated by neurotransmitters, which is we're going to open sodium channels and we're going to trigger action potentials in these nerves. So here's a picture that shows us a few of these here. And I lost my mouse pointer. There it is. All right. So we have, of course, a couple of things we want to point out here. There are three layers to the skin, right? We have the upper outer layer, which is the epidermis. And then we have below that the dermis. And then below that would be the subdermal tissues, fatty tissues and stuff like this, right? And so we have here, if we look up at the very epidermal region here, labeled pain receptors, these are things that are those free nerve endings. And you can kind of tell there that there's not much to them other than just looking like dendrites a little bit, right? And that's kind of really what they are. They're just like small little dendrites. They have little tips at the end of them that will detect any pressure and respond accordingly. But once we get into the dermal layers, we see that there are these other elaborated nerve endings, right? So this little thing here in light blue called a Meissner's corpuscle, that is a structure now that will detect pressure on the skin directly, right? And any pushing and stretching of the skin that occurs at that exact location will stimulate the Meissner corpuscle. Then there are Ruffini endings. Those are the ones highlighted in green there, which have a slightly different shape, right? And then deeper down in the skin, we find even bigger of these weird elaborated nerve endings called Pacinian corpuscles, right? And so they have a similar shape as the Meissner corpuscle, except they are kind of larger and flatter, right? So these different so-called corpuscles and other endings, they work differently. And so let's understand that, for example. So let's take a look here. So these so-called free nerve endings, they are on neurons that will have sometimes myelinated axons, but in many cases, actually, this is part of the pain channel. Sometimes there's no myelin on these pathways, or very little myelin on these pathways. It's a curious thing. We'll talk a little bit more later about why and how this works differently, that some of the pain pathways are unmyelinated. We find them here in certain locations, right, around the base of hairs and hair follicles, and pretty much all over the skin, though. So this is kind of one of those ones where we find them all over the body, whereas some of these receptors, they're only found in hairy skin or hairless skin. So we'll talk about that too here. So as I said, primarily these free nerve endings are about pain. That's what the previous diagram was showing, is labeling them as pain receptors. They also seem to detect warmth and cold as well. So we can essentially call them temperature detectors, although of course it's worth pointing out that the way our sense of touch works is that we're not quite so good at detecting absolute temperature values, right? We don't normally have a good ability to put our hand on something and say, oh yeah, that's 40 degrees or that's 80 degrees. Instead, we just say it feels cool. That's usually because it feels cool relative to our body temperature. And if I touch something and I think it feels warm, it's because it perhaps is a little bit warmer than my body temperature, right? So it's more about relative temperature differentials. We also have receptors that are within the hair follicle itself. You probably should be able to experience this quite so well as well, because you can check the hair in case on your arm. If I run a pencil over the hair on my arm, and I'm not touching the skin at all, right? But I'm just moving those hairs around. And if you don't have a hairy arm, then just try it up on the top of your head. If you just touch a little bit of the hair on your head without touching the skin, you can feel that, right? And of course, that means that any little pulling of the hair and shifting of the hair position causes a bending at the hair follicle where it attaches to the skin, right? And of course, there's a receptor there that detects this, right? So clearly, we only have these anywhere where we have hairs on the body. There are some places that are considered to be hairless skin, right? This is where we find now Meissner's corpuscles, right? The hairless areas of the body, where's that? Well, palm of your hand is a good example of this, right? So all of the palm, the base of the front side of the fingers and fingertips, lips as well, right? These are all hairless skin. And so this is where we have a particular kind of sense of touch that might be a little bit different than hairier skin. And of course, it has a lot to do with the way the Meissner corpuscles work, which is very different. As noted here, it detects sudden displacement of the skin, right? Let's move my computer, sorry. Of course, again, sudden displacement means I suddenly poke the skin, and that's a sudden movement or change in position of the skin. That's going to activate the Meissner corpuscle. Low frequency vibration or flutter. Now, what are we talking about here? I need a different crop. So I'm going to, get up my spiral notebook, right? And I'm going to run my hand across the metal spirals of the notebook, right? And I can feel that. I can feel that ridged texture of these things. But if I imagine what's actually happening at the level of the skin that gives me the ability to feel this, is it's a rapid change in the position of the skin. So there's that sudden displacement, right? But it's happening in a way that's very repetitive. And it's that repetition of pressure, no pressure, pressure, no pressure, as my hand moves over, that creates a vibration on the skin, right? And that's what that feels like. I can use the vibration of that. Now, of course, this refers specifically to low frequency vibration, so a slower vibration on the skin. Pacinian corpuscles also work very similarly to Meissner's corpuscles, except they detect a high frequency vibration. So what's the difference there? Well, when do we experience high frequency vibrations? When I touch something that is very, very textured, and I move my hand over it very quickly, I can rapidly detect that high frequency vibration as a coarse texture. If I am moving my hand over something that has more of a, let's think of it this way, I'm going to hold my phone now as a prop. And as I move my hand over this, there's a pattern of repetition that occurs because every time I hit the corner of the phone with my hand, there's a pressure and displacement of the skin, right? But it's happening slowly because these corners of the phone are fairly far apart. And that's a very low frequency vibration, right? And of course, it's useful if I want to detect the shape of an object to wrap my hand around it and cause this repetitious pattern. But I do it with the palm of my hand, right? I'm not very good. If you wanted to blindfold people and have them hold an object like this in their hand, they could very accurately do this and judge it's a rectangular object, maybe even understand that it's a phone. But if you blindfolded someone and placed it on their arm like this and just started rolling it over their arm and say, tell me what this is, they're going to have no idea that it's even a rectangle, most likely, right? And that's because there's not really any mycin corpuscles there to detect those patterns as quite so accurately as in the case of the Pacinian corpuscles, which are found both in the hairy and the hairless skin and detect those textures, right? And of course, if I run the spiral notebook over my upper arm here, I can detect that textured pattern just as well on my arm as I can with my fingertips, right? Because I have Pacinian corpuscles in both places. What else we got? We have Merkel discs, right? And so Merkel discs are also like Pacinian corpuscles found in both hairy and hairless skins. And here we get tangential forces across the skin. So what's an example of that? I'm going to come back to my phone here, and I'm going to just move it across the surface of my hand like this, right? That is a tangential force, right? It's a shearing movement across the skin, right? That works best, for example, what I do with my pencil. I'm going to come back to my pencil here. I take the pencil eraser and I push it somewhat hard against the skin, but try to move it sideways as I do so. That's really stretching the skin really hard. That's a shearing force. And that's what we're going to get here with the Merkel disc here. We can feel that kind of disturbance on the skin. As it turns out, Ruffini endings do something quite similar to that. So they detect the skin stretching. That's also what I said earlier when I talk about if I want to make a fist and the skin on the back of my hand stretches over my fingers, or if I close my elbow, the skin on the back of my elbow also then stretches. We're going to get that skin stretch detected by Ruffini endings. So clearly then Ruffini endings are playing an important role, not so much in our sense of touch on an object per se, but more about the position of my arms or my legs, right? Any moving part where the skin bends and stretches, it's going to activate these Ruffini endings. And now we have Krausen bulbs. We have them mostly in hairless skin. We don't have very many Krausen bulbs, as it turns out, and so we don't actually know a whole lot about them. So primarily they've been found in hairless skin, but there could be some exceptions to that, right? And clearly we don't know exactly what they do. Now there's some evidence to suggest that they are cold receptors, right? So when we're touching something cold, they are activated, right? But clearly our sense of cold doesn't depend entirely on them, because since there are known areas of the skin that do not have Krausen bulbs, and we can still feel a cold stimulus in those regions of the skin, that means that their exact role in all of this is clearly only partially related to that, right? And so their exact function, as I said, we don't entirely know. But beyond these receptors that we find throughout all the various kinds of skin surfaces that we have, we know that then that we go through the spine, right? So of course we have two different components here, right? We have the cranial nerves and we have the spinal nerves. I got confused by my own notes there for a second. That's why I paused. So of course there's skin on your head and face, right? And that means that the receptors on the skin of your head and face are going to go into the central nervous system directly into the brainstem through the cranial nerves, processing that information. But when it comes to all of the stuff below the head, neck down, that's going to go in through the spine. Right? And so we have all these multiple spinal nerves, and that's going to then integrate this information. If you remember, we've talked about how the spinal nerves are subdivided with a dorsal root and a ventral root. And it's the ventral root that carries the motor signals, but it's the dorsal root that brings the sensory input in. And that's what we're talking about here, is that for these spinal nerves, the dorsal root will be the nerve path that all of that touch information and even pain receptors and everything is all coming in through these dorsal roots. So here we have a little bit of a view of the spine here, showing us the some of the facial nerves here, and also what are the cervical nerves. These are the spinal nerves, right? So we have the cervical nerves here, cervical spine, are the first few vertebrae here. Then there's the thoracic spine. And so we have 12 of the thoracic nerves. This feed into different regions from the torso. The lumbar nerves, 5 lumbar nerves down here, and so different nerves feed in from that. And then we have the sacral spine down here, so we get 5 more nerve roots in that region of the spine. And then finally down at the coccyx, we have the coccygeal nerve, right? So there's just one pair of the coccygeal nerves. So these nerves kind of feed in. You can kind of see in this diagram how the spine is protected within these joint facets and the vertebral bone itself, the vertebral body, right? Cushioning between the vertebrae are these jelly-like discs that provide their cartilage, but they have like a jelly-like filling in them that provide that cushioning. But then in these little gaps between the joint facets here, these are the entryways for the spinal nerves. And you can see kind of just barely here in this diagram how this nerve branches to 2 different roots, right? And there's one that is going towards the belly side, the ventral side of the spine, that would be the motor signal, and the one going towards the dorsal side would be the sensory nerve. From here, one of the things that we want to talk about these spinal nerves, I've got the dorsal and ventral root breakdown there. That was also called the Bell-McGindy law that we'd covered that there, the research of Charles Bell and Francois McGindy. But there's also this idea of a dermatome. And I know we covered this in one of the earlier chapters as well, but the idea is that the dermatome refers to the area on the skin that is innervated by that particular nerve. And so this is a kind of a pattern of concentric circles on the skin, so that any one of these spinal nerves is monitoring some region somewhere of skin on the body. And this come in through these different spinal nerves. We get all of the various regions of the body surface covered there. And then of course, it's going to go on up to the brainstem and further into the brain. As I noted earlier, the touch pathway and the pain pathway remain somewhat distinct as they travel into the spine and then up to the brain. And of course, there's a difference there between the myelinated neurons and the unmyelinated neurons. And then we're going to go to the cortex. But for now, what I want to do is go ahead and cut it here now that we've kind of covered the more peripheral side of somatosensation. And before we go on into the more central nervous system processing and talk more about the details of the pain pathway, this is a good place to cut it.